Today we're going to look at KEMET's latest product,
METCOM power inductors.
Hi, my name is William from the KEMET Application Intelligence Center, and with me is my good friend and colleague, Wilmer.
We have been teasing an exciting power inductor product launch for some time now, and this is it. We get many requests from customers asking if we have power inductors available in a specific set of footprints and inductance values. After doing some searching, I would unfortunately have to say no to them, but those days are over. We have officially released METCOM power inductors, which are available in a wide variety of popular footprints and inductance values.
It's always been a challenge to find part alternatives when your design is nearly finished or when you're looking for specific inductance.
It sure is. KEMET has been investing heavily in a drop-in replacement for frequently used power inductors.
Let me get this straight. I can use even more KEMET parts on my design now? That's awesome. How many footprints does KEMET carry? How many parts have been added?
Whoa, easy there, kiddo. We'll get to that in a minute. METCOM has added 102 new and unique power inductors to KEMET's catalog and will come in these form factor groups: 5x5 millimeters, 6x6 millimeters, and 8x8 millimeters, all ranging in height from 1.8 millimeters to 5 millimeters.
I'm intrigued. Let's hear more.
The METCOM series are metal composite surface mount power inductors. It has a shielded construction with inductance ranges from 0.1 microhenries to 47 microhenries at 100 kilohertz and a tolerance of plus or minus 20%. From a current perspective, the METCOM power inductors are rated between 2 amps and 35.4 amps. The DC resistance ranges from 1.5 milliohms to 341 milliohms. And finally, the METCOM's operating temperature range is from minus 55 degrees C to 155 degrees C.
Wow, 155 degrees Celsius. We're really making sure these parts don't fail in heat.
Yeah, you know what they say, if you can't stand the heat, get off the PCB.
All right, let's do a quick sort based on inductance and footprint size. This will give us a good visual of what KEMET has to offer. In the gray, we have KEMET's initial 24 power inductors shown. It's pretty empty if you ask me. Now let's add the METCOM power inductor lineup to this plot. With 102 new and unique parts, we can see just how much more support we offer between the 5x5 millimeter and 8x8 millimeter footprint range.
The METCOM power inductor series certainly meets a lot of the criteria needed in the industry. We'll have more to come later, but we can't show you that just yet. Will is with me to show how these power inductors behave in a real application. Can you show me what you've prepared?
Of course. We can use these two TI evaluation boards. We have a couple of buck converters. I'll let you pick which one we try first.
And you're the winner.
The LM43603 PWP EVM evaluation board is a DC to DC buck controller. We'll be testing it using a 9-volt DC input voltage, which will be stepped down to 3.3 volts DC. It is designed with a maximum current of 3 amps and an operating frequency of 500 kilohertz. But first, we need to figure out which METCOM power inductor to use. Using the schematic, we can quickly identify the inductor used in the design, right over here. We can easily cross this part number on Component Edge, which is our component search engine that can be found at search.kemet.com. This gives us the MPX 1D0840L6R8.
Awesome. Now we have all the information we need to start our experiment.
We'll be testing with two types of loads: a constant load at 2 amps, which is the design's maximum rated current, and a dynamic load with current swings from 0.5 amps to 1.5 amps at a rate of 100 milliamps per microsecond. Here, the board is connected to a power supply, and here, the output voltage is connected to the DC load. We will also be using a power probe in order to measure the output voltage, and a current probe in order to measure the output current. We will start our measurements by baselining the performance of the original inductor. Let's turn on the DC load set at 2 amps. Now let's look at the oscilloscope and measure the output voltage. We see roughly a 3.3 volt output. That's good. Let's zoom in closer and see the ripple voltage. We get roughly a 12 millivolt peak-to-peak measurement. We also notice some inductive noise, which is not desirable, but it will not affect our comparison since we'll be using the same setup throughout the test. Let's retake the same measurements, both at dynamic load. Under a constant transient load, the peak-to-peak voltage is now at 130 millivolts. Finally, let's look at the temperature rise of the inductor after 30 minutes with the 2 amp constant load. The thermal camera measures the inductor to be relatively the same as the board temperature, at 30 degrees Celsius.
Let's replace the power inductor with KEMET's METCOM MPX power inductor that we found earlier on Component Edge. Wow, even I can't tell them apart.
Now let's run the same test again for the METCOM power inductor. First we turn on the static load, and then we measure the output voltage. We see 3.3 volts. That's a good start. The peak-to-peak ripple measurement is around 13 millivolts, and again, looks just like the original. Let's see how it does with the dynamic load test. And we see 130 millivolts, just like before. I'm starting to see a pattern here. Let's take the thermal profile of the inductor and see what we get. We can see that the METCOM power inductor and board temperature are at 30 degrees Celsius again, just like the original.
Everything is basically the same. I would not be able to tell from the electrical or physical data that these two are different. The thermal image helps us get a sense of the core losses, and the differences between the two are negligible.
We will test the last board the same way by replacing the original inductor with a KEMET METCOM power inductor. And with the magical help of video editing, we will be right back with the final results. We're back, and these are the complete results from our experiments. Now for the oscilloscope output of the second buck converter we just finished looking at. The TPS54336 with the NPX1D0840L6R8 also shows identical electrical results from the original inductor. Lastly, the heat signatures are also equal between the two. Just as we observed before, the performance stayed the same before and after the METCOM power inductor replacement.
It was very easy updating these boards and incorporating METCOM power inductors into these designs. The risk is very low since the performance is nearly identical. Now, KEMET can offer a great range of power inductor solutions with the high quality and customer support that we are known for with our capacitors.
Remember, KEMET is more than just capacitors. Now please remember to smash that like button and subscribe to our channel, get more information about new and upcoming products or content from Cake. Thanks for watching and stay curious.